Okay, shall we start, Vishnu?
Sure.
Hey, we are very pleased to have Challenger Mishra today from Cambridge, and he's going to talk about matrix and machine learning. Please.
Thank you very much for the kind invitation to talk at String Data 2021. Would have been nice to see everyone in person, but such are the times we live in. I'll be talking about metrics and machine learning. And before we get into that, for people getting into machine learning and new string theorists, I'd like to highlight some data sets and research directions that I find exciting. But even before that, let me mention briefly our research group at the computer lab in Cambridge. We are a brand new group of machine learners and scientists, and we have congregated at the computer science department. Our program is called the Accelerate Program for Scientific Discovery, and we have a bunch of activities centered around machine learning for science and mathematics. Please do check out our activities at the link. Now, machine learning and string theory have recently come together, and by recent, I mean very recent. There have been a lot of interest from machine learners and string theorists in recent times in trying to solve problems in their respective domains. In terms of when we speak about machine learning, there's always an underlying thought about data. And in string theory, there seems to be a large number of data sets that have appeared over the last few decades. So in particular, so here I have listed some data sets, their sizes, and the point of time at which they came about. So there are various data sets of geometries, for example, the complete intersection Calabi-Yau threefolds, which came about towards the end of the 80s. There's the Kreutzer-Skarka dataset of Calabi-Yau threefolds, which is the largest dataset of Calabi-Yau threefolds that is known. It's 500 million in size. There are datasets on supersymmetric bundles over Calabi-Yau manifolds, string-derived particle physics models. There are datasets on symmetries of Calabi-Yaus, datasets on complete intersection Calabi-Yau fourfolds, and various other geometric data sets. And new data sets are constantly being painstakingly created through mathematics, and machine learning string theorists have been working on these data sets and some others, with the first such papers appearing in 2017. In terms of research directions, initially there was a lot of interest in the community on understanding topological properties of stringy geometries. And there has been fantastic progress in that. Now there are machine learning architectures, in particular deep learning architectures, that can predict with very high accuracies topological properties of various geometries. Another direction that interests me is studying invariances of Calabi-Yau threefolds. These are quite important from a phenomenological point of view in terms of explaining phenomena that we see or do not see at the energy scales corresponding to the standard model of particle physics. There's a lot of data now on string-derived standard models, and machine learning is a new tool in helping us understand such data. There's one could study the moduli spaces of bundles over string geometries. One can also look at other interesting geometrical quantities, such as the metric on Calabi-Yaus, which is an important problem. This talk is primarily dedicated to looking at machine learning ventures in that regard. There are also various other big picture problems involving swampland conjectures and Reed's fantasy, building string theory models in a faster fashion, utilizing machine learning. Q2 work due to Fabian and Sven on some of these interesting problems. Right. I'm going to be talking mainly about our paper from last year, which I had the pleasure of collaborating with Vishnu Jajala and Damien Mayorga-Pina. This was our pandemic paper. This is what I personally will remember the pandemic as. There have been in the past various numerical approaches to Calabi-Yau metrics, work due to Hedrick and Weisman on approximating Ricci-flat metrics on K3 surfaces. There's also a rich body of work centered around Simon Donaldson's results in this context. There have been interesting developments recently on discovering analytic metrics on K3 surfaces due to Shamit Kachru and others. In terms of utilizing machine learning for understanding Calabi-Yau metrics, there was a paper that appeared by Anthony Ashmore, Yang Hui He, and Bert Overoot a couple of years ago. Following that, there has been a different approach on approximating these Ricci-flat metrics on Calabi-Yau spaces. There have been work by Douglas and company and Laura Anderson and company and as well as us. More recently, there's a new paper that has appeared due to Magdalena, Andre Lucas, Fabian, and Robin Schneider. So there's a lot of excitement in the field towards discovering Ricci-flat metrics or their approximations on these wonderful geometries. Now, string theory, to begin with, I'll briefly motivate why we are interested in such a problem and what are the outcomes that we expect from these approaches to approximating Calabi-Yau metrics. Now, string theory is the only known consistent theory of quantum gravity. It postulates 6 extra dimensions of space and relies on a fundamental symmetry called supersymmetry. As we all know, it is also an organizing principle for mathematics. Now, superstring theory supplies an architectural framework for obtaining the real world from a theory of quantum gravity, and there are various versions of string theory connected by dualities, and they are represented as islands in this beautiful tropical place. The field of string phenomenology is something that would ultimately rely on these Calabi-Yau metrics in making precise predictions about various physical quantities such as masses of particles and the spectra. Now, the holy grail of string phenomenology is to embed the standard model of particle physics within the framework of string theory, reproduce the particle content, coupling constants, masses, like I was mentioning before, explain the origin of discrete symmetries, explain fine-tuning, supersymmetry breaking, and unfortunately, there is no such model till date, but there has been considerable progress in building semi-realistic string theory models over the last decade or so. Right. Now, string theory reduces to this standard model of particle physics via an intermediate grand unified theory. This process is called compactification, and this process places severe geometrical constraints on the extra dimensions of string theory called Calabi-Yau manifolds. Now, Calabi-Yau compactifications of the heterotic string is one of the most promising avenues for string model building. The space-time is a direct product of a maximally symmetric space and an extra dimensional space X6, which ultimately turn out to be Calabi-Yaus. If we demand X6 be Riemannian, which is what we need to describe a theory of gravity, if we also want to describe chiral fermions, then the extra dimensions X need to be irreducible. And further, if you demand n equals to 1 supersymmetry in the 4-dimensional theory, then this sets the holonomy of the extra dimensions to be SU3. But do such manifolds exist? Thankfully so, and we have numerous examples. The Calabi conjecture, later proved by Yau, says that an n-dimensional complex scalar manifold with vanishing first-in-class admits a metric with this holonomy. And this leads us to the class of Calabi-Yau manifolds. Now, a lot of the phenomenological questions can be answered by studying the topology of the Calabi-Yau geometries alone. For example, in certain settings, the number of generations of particles that you obtain in your underlying standard model could be related to to a topological property, namely the Euler characteristic of these extra-dimensional spaces. More generally, bundle-valued cohomology groups can compute particle spectra, and there are lots of constructions on building string theory models over Calabi-Yau spaces, and some of these constructions involve describing bundles over these spaces. Now, depending on the kind of bundle you choose, you get a different kind of grand unified theory group. And although we do not know what the gauge group of the grand unified theory is meant to be, there are various possibilities depending on the kind of bundles one works with. Now, prior to 2008, only a handful of string-derived standard models existed. Later, due to a wonderful construction by Laura Anderson and James Gray and Andre Lucas, later on Yang Hui He and Andre Constantine and others, there have been tens of thousands of semi-realistic string standard models, and these constructions depend on the choice of a vector bundle to be a line bundle sum. And there's a lot of things we understand about the topology of these constructions, but in order to fully analyze these models, one would need knowledge of the metric on your underlying geometry X. Let me present a vanilla string model that I worked on with Andre Lucas and Andre Constantine during my PhD. Here, I'm simply, without really going into details, writing down a string model where V is a bundle, a line bundle sum defined over this nice Calabi-Yau X. This is a complete intersection Calabi-Yau, and the model itself is built not on the base geometry, but on its quotient by this discrete symmetry group gamma, which is a semi-direct product of Z4 times Z4. Now, this is one of tens of thousands of string theory models that lead to a grand unified theory group with gauge group, grand unified theory with gauge group SO10, and it reproduces many features of the standard model. And again, none of these models give a complete picture, but simply lead to semi-realistic string models that agree with the standard model in broad terms. The reason we looked at these kind of guts with these gauge groups is that they are motivated by the fact that that neutrinos are not massless. So topology on its own is a sufficiently powerful tool to enable string model building to a very large extent. But to go beyond an analysis of the particle spectra, we must obtain the Kähler potential that leads us to the underlying flat metric on the Calabi-Yau. Now, knowledge of this metric will ultimately lead to computing masses of fundamental particles in this context, and determining physical quantities, therefore, from first principles, requires an understanding of the geometry as well as topology of these Calabi-Yau spaces. There are many possible Calabi-Yau geometries, and this is a plot of around 500 million of these geometries. And there are different approaches to string theory which involve different geometries, but we focus on Calabi-Yau threefolds. And for the purposes of a machine learning approach, we look at some of the simplest geometries that are possible, and they come from the list of complete intersection Calabi-Yau threefolds. Now, these complete intersection Calabi-Yau threefolds, or CCs in short, they can be represented by some configuration matrix, which give you multi degrees of polynomials with coefficients in a product of complex projective spaces. And simple conditions on these degrees determine whether such a configuration matrix can represent a Calabi-Yau threefold or not. An example of this is the pharmaquintic, which is listed at the bottom. It is simply a degree 5. The geometry is described by a degree 5, the vanishing locus of a degree 5 polynomial on CP4. Here are a couple of examples of this class of manifolds, and they lend themselves easily to nice bipartite graph representations as well. They look very beautiful and symmetric, and many such geometries have led to semi-realistic string theory models. These geometries are also connected by conical transitions, or more generally geometric transitions, and they provide a beautiful geometric picture for the class of Calabi-Yau, a complete intersection Calabi-Yau manifolds. Now, as a complex scalar manifold, the metric of a Calabi-Yau is a Hermitian matrix that can be derived from some potential k. So one simply takes derivatives of the potential to obtain the metric, which then can give you the Kähler form J, which is closed, and the corresponding Ricci tensor is given by this very terse expression in terms of the determinant of the metric. And a Calabi-Yau admits a metric with non-vanishing Ricci with vanishing Ricci curvature, and it is unique in each Kähler class. And as I mentioned before, till date there have been no analytic expressions that have been found for a Calabi-Yau for a Ricci flat metric of a Calabi-Yau threefold. In our paper, we looked at a bunch of examples. We looked at the K3 surface. We looked at the pharmaquintic, the Dwork family of quintics, as well as the Tian-Yau. We have been successful to various degrees on these geometries, and I'll mention details of our approach in the coming slides. We also note here that we look at the Tian-Yau manifold in particular, and a freely acting Z3 quotient of this manifold yields an interesting geometry on which there have been constructions of string models. The transpose of this geometry is also another complete intersection Calabi-Yau, and namely the Schoen manifold, and this admits different kinds of representations or other embeddings embedded in products of projective spaces. And these various representations can be related to each other by splittings and contractions. Now, the methodologies that we have utilized so far and in our upcoming work are as follows. Donaldson's algorithm, as I mentioned earlier, is one of the early approaches to determining such a numerically approximate Ricci flat metrics. Many others and ourselves, we have looked at neural networks for PDEs, and we also look at Kähler-Ricci flow and look at energy functional approaches. Now, to begin with, we employ neural networks to solve a PDE that is satisfied by a Ricci flat metric. Now, this involves several steps. One might ask, if you're employing machine learning, where is your data? We have no data. But the data is actually required to compute some volume integrals. And for that, one of the important and key steps is to generate points uniformly over a geometry. Later, I move on to describing benchmarks that we use to understand how well we did on in terms of how flat a metric we obtained. Then I explain or show you the kind of machine learning architectures we have used. In particular, we have utilized neural networks, but we also have a modular approach. We employ multiple neural networks which are then combined to give a description of a metric. And let's proceed. So
I have about 5 minutes.
Sorry?
You have about 5 minutes.
Oh, okay. I'll speed up. So this first key point in this entire machine learning venture is to generate points uniformly on a Calabi-Yau. And we employed a procedure that's been used by others, and it comes from this interesting work by Schiffman and Geldich. And in summary, this is explained quite neatly for a simple situation. For example, the pharmaquintic. The idea is to sample points uniformly on a sphere in the ambient space with respect to the Fubini-Studi metric. And further, we join up these points on the sphere, and we choose these points randomly and draw lines through them. When the lines intersect the Calabi-Yau hypersurface, then we choose that point, and therefore the points sampled in this way are uniformly distributed with respect to the pullback of the Fubini-Studi on your hypersurface. Here's an example of points generated on the complex torus in this fashion. Here, 3 Riemann sheets are glued together by branch cuts, and Damien has created this beautiful plot. One also has to be cognizant that there is no uniform coordinate system that can describe the entire geometry. So we need to deal with a description. We need to deal with different patches on this geometry that cover these geometries and sample points from all those patches. The neural network architecture we employ is modular, mainly because the metric, which is positive definite, lends itself to a decomposition. Namely, we use this LDL decomposition, where D is a diagonal matrix and gives information about the eigenvalues of the metric. And the lower triangular matrix L contains some off-diagonal entries, which we model by a separate neural network. And we combine these the outputs of these networks to reflect the decomposition and end up with the metric G. The inputs to this architecture are points on the geometry that we have uniformly sampled. The loss function that we employ in training this network has 3 main components. One is the sigma measure, which one can show when sigma measure approaches 0, that the metric is indeed Ricci flat. And it essentially tells you, compares 2 different ways of computing the volume. The second component of our loss function determines how scalar is our metric. We actually model the metric directly instead of the potential, so we have to be particularly careful about this. The third component of our loss function is the mu measure, which ensures when the mu measure is 0, it ensures that there is agreement of the metric on the overlap of different patches. So when we combine all these 3 losses and employ our architecture, when the loss is 0, we would have gotten a Ricci flat metric. But of course, in machine learning, that would be extremely rare. So we deal with approximate Ricci flat metrics. Now to come to some of our results, here we show the 3 losses on the pharmaquintic. The first, let's look at the first row. We plot the sigma measure, the kappa measure, and the mu measure. And during the course of training, we see that all these measures are decreasing. And the 3 rows correspond to 3 different activation functions that we have used. We have similar results and trends for the dwarf family of quintics, which is a 1-parameter family of quintics and is an interesting geometry in itself. Finally, we also look at the Tian-Yau manifold. Of course, here we have not done a complete job because we did not have a handle on scalaricity, nor did we insist that our metrics should be in agreement on the overlap of different patches. So here we only look at the one of the measures. So we switch off two of the parts, components of our loss function, and we focus only on the sigma measure. And the top row denotes how training went when we sampled utilizing a symmetry in of our equations that we specifically chose for our Tian-Yau case. And the bottom set of plots shows the same learning procedure without taking that symmetry into account. Now let's quickly come to Ricci flow. I'll take a couple of minutes to wrap up. In Ricci flow, you essentially have another way of arriving at Ricci flat metrics. And geometrically, what Ricci flow does is the following. It tries to uniformize curvature. So if you have a loop where curvature is not uniform at every point, it tries to reduce the curvature on points that are bulging outwards or of positive curvature, and it tries to pull out points which are of negative curvature. And ultimately, if you also preserve the volume inside, then you get a nice circle. And if you apply the same approach to this delicious donut, then you arrive at this long candy cane. What happens is the outer part of the donut essentially has positive curvature, so that's squeezed in, and the inner part of the donut has negative curvature, so that's squeezed outwards. And ultimately, in the limit, when you have completed Ricci flow, then you essentially get an infinite cylinder. Thanks to Andrew Dancer for making that picture clear to us. Now, in Ricci flow, essentially, it gives us a set of differential equations that involves the metric and another function, namely the dilaton, which and these differential equations, which we are planning to solve or emulate on a neural network, they come from some functional, namely the Perelman functional, which has very nice properties, including admitting a gradient flow. The starting point of the flow is the Fubini-Studi metric, which is an analytic metric that we know that comes from the ambient space, and there's a beautiful description of this in terms of a potential as well. And the final approach that we are exploring as follow-up to our original work is an energy functional approach. Some work has gone into this, and here we look at directly minimizing functionals involving the metric, and the kind of outcomes we expect, and some initial experiments we have done are shown in this graph, are shown in this slide. Namely, on the left-hand side, the donut essentially has different curvature at different points, and at the end of the flow, we expect uniform curvature all along the torus. And in one of our numerical experiments, what we found is if you take a slice of the donut, a cross section, you realize that the curvature only depends on cosine theta, theta being the angle that parameterizes that circle of cross section. And we see that to begin with, we had periodic curvature on along this cross section, but during the course of Ricci flow, we see the curvature uniformizing and approaching zero. In the future, we expect to continue working in this direction. So we want to emulate Kähler-Ricci flow on neural networks. We are looking at different energy functional approaches. We'd also like to look at how Calabi-Yau metrics transform under geometric transitions. And we're also looking at discovering flat metrics on other Calabi-Yau constructions. A lot of this is work in progress, and in some of these cases, we are at a very preliminary stage, and there's nothing super exciting to report at this stage, but we expect to show some work in the coming months. Thank you very much for allowing me to speak.
Excellent. Thank you very much for brilliant talk. We have a very short time for one or two short questions. Steve, please.
Yeah. Hi, John. Thanks for the the very interesting talk.
Hi,
So
Sven.
can you say a bit more on the Ritchie-Flow story, what your experiences are, and in particular, what I'm interested in is to hear some comments on efficiency that you're encountering in comparison to the other methods.
So on Ritchie-Flow, of course, it gives you a set of a couple differential equations which have come from some variational principle, from some functional. So the kind of stuff we are exploring is not to solve these differential equations numerically, but to actually try to emulate them on some neural network, which means mapping the flow equations in a clever fashion to mimic the training on a neural network. And we have made some progress in that direction. My PhD student, Justin, is also working on this, and we have other collaborators on this, Damien, Vishnu, and Orgho Chattopadhyay, who is at WITS. So far our experience has been that it looks promising, and perhaps it's showing a better way of doing Ritchie-Flow in comparison to numerically solving these differential equations. There's also some difficulties related to solving these differential equations irrespective of the approach. So one of the issues is the flow equations that appear from this, the metric, they look like heat equations, but the differential equation for the metric is a forward propagating differential equation, whereas the differential equation for the dilaton has to be propagated backwards in time because there is no guarantee for existence of solutions for arbitrary starting points of the dilaton. So, and we are also looking at an energy functional approach where we directly try to minimize the functionals that appear using a host of optimization techniques and ML architectures.
Thanks.
Okay, thank you very much for your excellent talk again. We are going